Welcome back to another exciting lecture of CS152. This is one of my favorite topics in all of computer architecture, achieving correct pipelining so that we can get the best performance out of the silicon resources that we have. So yeah, let's see if I can do a very good job of keeping it exciting as it actually is. Okay, at the end of the last lecture, we saw a problematic example which could provide us with wrong answers if we tried to pipeline things, I guess, naively. Just to slightly quickly go over what the example was, what we were going to do is load some immediate value, the address of the data label, data, load an immediate value to T0, and then treating the value inside T0 as an address, because it is an address. Treating it as an address, we will load the first word from the data section, and then the second word from the data section by giving it an offset of 4. So at this point, S0 and S1 will have 1 and 2 stored within it, hopefully. And after that, we will add S0 and S1 and store it into S2. So adding 1 and 2 ideally should give us 3 stored inside S2. And after this, we should be storing, we want to store S2 in the third slot of the data section, denominated by the offset of 8. So after this execution, we want 3 to be stored after the 1 and 2 data elements already stored in the data section. So after the execution of this whole thing finishes, what we want stored in memory is 1, 2, and then a new word, 3, stored in the data section. But we said that assuming that the register file is initialized to 0 at the beginning of time, after this execution with the pipeline that we designed in the last lecture, what would actually be written would be 0. The reason for this is hazard, which is what we're going to be talking about at today's lecture. So there are multiple types of hazards, but the first hazard we're going to be looking at, because that was the big thing that affected the previous example, the first hazard we'll be looking at is what is called the read after write hazard, raw hazard. And this happens when an instruction, a later instruction, depends on a register value updated by a previous instruction's execution results. So here's a simplified example to describe a little bit more intuitively what that means. So let's say we have 2 instructions. We have 2 instructions. The first instruction takes the value inside S1 and S2 and adds them together and stores it in S0. The second instruction takes the value of S0, which was calculated in the previous instruction, adds it to S4, and then stores it to S0. So there's a shared register between these 2 back-to-back instructions. So what would that look like in our naively implemented pipeline? So in the very first cycle, we have instruction 1, which is the red block, coming into the system. So we fetch the instruction for S1, we fetch the instruction for instruction 1. And at the next cycle, this instruction would have moved on to the decode stage. So in the decode stage, the instruction, if the instruction does any register reads, the register reads will be satisfied from the register file. So at the second cycle, instruction 1 will read S1 and S2 from the register file. And then at the third cycle, first instruction, at the second cycle, S2, the instruction 2 would have been fetched. And at the third cycle, the first instruction has now moved on to the execute stage. And at the execute stage, it is calculating the value for S0, which it will write to S0 when the instruction 1 reaches the write back stage, because the only data path that writes anything to the register file exists at the write back stage right now. So in the third cycle, instruction 1 is just now calculating the value it wants to store to S0. But unfortunately, at this point in time, instruction 2 is now at the decode stage. And if instruction 2 doesn't know whether the previous instruction is still calculating S0, it doesn't know, or if there's no data path that lets instruction 2 know about any of this. So instruction 2 at this point is just happily asking the register file to give it values that it has for S0 and S4, which are the input operands for its own add operation. So at this point, at this point, the value for S0 has not been written back to the register file yet. So the effects of instruction 1 will not be visible to instruction 2 quite yet, which is not what we expect from which is not what we expect to happen when we're writing this kind of assembly code. So here's another example. Simpler example. So we have two instructions again. One instruction is add immediate. It adds 1 to the 0 register. So we're going to be storing 1 inside S0. And the next instruction is the number 0 should be reading 0, spelled out 0. The next instruction is adding 0 to S0. So what we expect from this code to happen is after the first instruction finishes, we want the value of 1 to be stored inside, add immediate, so that the 0 is correct, sorry. After the first instruction finishes, we want the value of 1 to be stored inside S0. After the second instruction, we also want the value of 1 because we're adding S0 to nothing. We also want the value of 1 to be stored inside S1. So after executing these two instructions, S0 should be 1, S1 should be 1. That's what we expect. Unfortunately, let's walk through the instructions. At the first cycle, the first instruction is injected into the fetch stage. So the requests for instruction 1 from memory is sent out. At the second cycle, the instruction is read. Instruction 1 is read. Now it's inside the decode stage. So it reads the 0 register, and the immediate values of 1 is decoded from the instruction. Meanwhile, the second instruction, the blue box, is injected into the fetch stage. So the memory requests for instruction 1 to read the encoded instruction of instruction 2 is sent out from the fetch stage to the memory. At the third cycle, instruction 1 is now moved on to the execute stage, and it calculates the value that it will write to S0 eventually. S0 is still 0 at this point. S0 as it is written inside the register file is still 0 at this point. So at the third cycle, instruction 2, because one of its operands is S0, instruction 2 reads the value of S0 from the register file. But because instruction 1 has not reached the write-back stage yet, the value of S0 that instruction 2 reads is still 0, because the value of S0 as stored inside the register file is still 0. So it goes on. We read the wrong data, but because the pipeline intuitively, it's not like the pipeline implementation knows intuitively what we as CPU architects wanted. So it just happily is moving data through the pipeline. So we are moving wrong data through this whole pipeline until the instruction 1 reaches the write-back stage. And only after the instruction 1 is retired from the write-back stage, the correct, so to speak, answer for S0 is now available from the register file. So obviously, we're getting high performance because we're processing one instruction per cycle. But there are situations you can see that we will get wrong data. We will get wrong answers from the one that we expect. And I guess there are some convoluted cases where people argue for performance at the cost of accuracy. But at this level, we're not talking about that kind of stuff. So this is not what we want. So how do we solve this problem of having read after write hazards? The first, maybe one of the most obvious solutions to this is stalling the pipeline, called stalling. The processor can choose to stall the decoding stage, to stall instruction 2 from reading the values from the register file when the processor detects a read after write hazard. So let's see how we can implement stalling in this pipeline. So it's the same instructions as before. Instruction 1 is injected into the fetch stage. The instruction read request is sent out. At cycle 2, instruction 1 has been read from the memory. It's been decoded. Instruction 1 reads S1 and S2 from the register file. And at this point, the CPU, the processor, if we implement the logic for it, now knows that instruction 1 wants to write to S0 eventually. And with that in mind, with the processor keeping that in mind, when the second instruction comes in, it can be just held at the decode stage because the processor now knows that a previous instruction, instruction 1, wants to write to S0, and instruction 2 wants to read from S0. So it knows it can make the decision that in order to get correct results, instruction 2 can just be held at the decode stage without actually moving forward, without actually reading from the register file until the effects of instruction 1 has been applied to the register file. So all the way until cycle 5, it'll just be kind of stuck there. And only after instruction 1 has retired and the results of instruction 1 is now visible from the register file, instruction 2 can only then read the results from the register file and is allowed to move forward. And what happens here is that there are some cycles while the instruction 2 is stuck inside the decode stage, instruction 1 has moved on and on. And meanwhile, while instruction 2 is stuck inside the decode stage, the execute and memory stages don't have useful work to do. It's just at every cycle, it's saying, I still don't have work to do. I still don't have work to do. So this is called a pipeline bubble because we have pipeline stages that are not actually doing any useful work. These are called bubbles. And bubbles are bad because that represents low performance. And I just noticed there's a question explaining that part one more time. Which part do you mean? Sorry, I guess I moved forward without the previous page. Let's see. All right, let's look at this. Oops. Yeah, so we're looking at a naive pipeline implementation without any special handlings of hazards. So this is the implementation we're looking at right now assumes that, well, I guess it doesn't assume, it just doesn't know about the existence of hazards. It's just going to happily keep moving pipeline instructions forward at every cycle. And I'm going to, this is going to show that that actually results in wrong results. So again, just to quickly go over the instructions, there's two instructions. Instruction 1 is an add immediate instruction. So it adds a register value and an immediately encoded numeral. So the instruction 1 adds 0 and 1 because the 0 register always returns 0 in RISC-V. So the instruction 1 adds 0 and 1 and writes it to S0. So after this instruction, we should have 1 stored inside S0. And instruction 2 does the same. It's another add immediate instruction, but it adds S0 and 1. So S0 and 0. So at the end of instruction 2, what we should have is basically moving the value of S0 to S1. So after these two instructions finish, we expect S0 to hold 1 and S1 to also hold 1. But because there is a read after write dependency, because instruction 1 writes to S0 and instruction 2 reads from S0, and they're back to back, without special handling for read after write hazards, the results we get are going to be wrong. So let's see. At the very first cycle, instruction 0 is being processed by the fetch stage, and what the fetch stage does is it sends out a memory request to the instruction memory, to the program. And at the second cycle, the memory read request has come back, and the decode stage has decoded the encoded instruction. It knows what kind of instruction it is now. It knows which registers it must read from. It knows a bunch of other things. So instruction 1 is inside the decode stage, and at this point, I didn't write that down here. At this stage, instruction 1 has read from the 0 register. And so, yeah, it has read from the 0 register. And at the next cycle, at the previous cycle, sorry, I keep spending time here. At the previous cycle, the instruction fetch for instruction 2 has now also been sent out. And at the third cycle, the instruction fetch results have come in for instruction 2. So the instruction encoded form of instruction 2 has now been read from instruction memory, off-chip memory, or cache, whichever, into the decode stage, and it's being decoded. And at this point, the instruction 2, the processor knows what kind of instruction 2 is, if it should read register file data, which one should it read, etc. So at this cycle 3, the decode stage is processing instruction 2, and that also involves reading from S0, from the register file. But unfortunately, instruction 1 has not yet reached the write back stage, which means the add results 0 plus 1 that instruction 1 should have done, is doing inside the execute stage, only the execute stage knows about yet, because it has not been written to the register file yet. There is no path from the execute stage to the register file in the processor that we designed. So the answer for the add immediate instruction exists somewhere in the processor. It exists in the execute stage, but it has not been moved to a position that instruction 2 can access yet, because the instruction 2 only looks at the register file. But the add immediate instruction results has not been applied back to the register file yet as of cycle 3, as denoted by all of this here. At each of these cycles, the value of S0 as it is visible from the register file has not been updated yet. So instruction 2 at this cycle 3, reads from the register file, reads S0 from the register file. But because the value of S0 as stored inside the register file is still 0 at cycle 3, what instruction 2 reads would be 0. Even though from when we were writing this code, the code above, what we expect I2 should be reading, instruction 2 to be reading, is 1, because we expect S0 to be holding the results of the add immediate instruction, which is instruction 1. So at this point, we already know that the answer is going to be not what we expect, because instruction 2 has read data which we do not expect, we have not expected. But yeah, so at this point, everything's just wrong. But just we can keep going to see what happens. At cycle 4, instruction 1 has now moved to the memory stage, but instruction 1 doesn't have any memory accesses, so it's not going to do anything there. Instruction 2 has moved to the execute stage. It's going to perform the add instruction, the add operation using the ALU inside the execute stage. But because the S0 as read in the decode stage is 0, the results of the add instruction is also going to be 0, even though when we were writing the code, we expected the add instruction to have a result of 1. So we keep going, and at the end of the write back stage, as the first instruction is retired, S0 is now finally updated. But it's too late for the instruction 2, for that result to have any effect on instruction 2, because instruction 2 has already read the value of what it thought was the correct value of S0 back in cycle 3. Right, and I guess after this stage, S1 will also be updated by instruction 2, but that's also going to be wrong. We expect S1 to be 1, but we're only going to get S1. The S1 value is also going to be 0. So I guess after the end of all of this execution, we expect S0 to be 1, S1 to be 1, but if we wait a long enough time for this to finish, S0 will eventually become 1, but S1 is going to stay 0. So it's a wrong state we fall into, and we want to avoid that. So we talked about stalling. But here, let's look at another. Yes, we talked all the way up to here. Right. So if the processor somehow knows that we have circuits, we design and implement circuits inside the processor to keep track of the destination registers of all instructions that are currently being processed, and somehow reference that for all instructions that come into the decode stage. Okay, bubbles. Yeah, if the processor, keeps track of all the destination registers of all the instructions in the pipeline, and we cross-reference that if we implement the circuits to cross-reference that for every instruction that goes into the decode stage, so that we don't actually allow this instruction to move forward from reading the register file, moving into the execute stage of whatever, until all of the previous instructions that which writes to the register files that the current instruction depends on. That was a mouthful. So if I try to put it in a more simpler English, if a previous instruction writes to S0, any of the previous instructions that are still inside the pipeline, that are still not retired, writes to S0, and the current instruction that is inside the decode stage wants to read from S0, the processor is going to keep it there, keep it inside the decode stage until all the instructions that are currently inside the pipeline that wants to write to S0 has been retired. So that's what happens. Let's go back to yes. So instruction 1 here wants to write to S0. Instruction 2 wants to read from S0. So in a stalling implemented processor, S2 is going to be stuck inside the decode stage. It's going to wait to read from the register file until instruction 1 actually finishes writing to S0. And because at every cycle, and I'm going to have a slide after this that steps through these cycles in a little bit more detail, but let's see. Because instruction 1 keeps moving forward while instruction 2 is still stuck here, execute and memory stages are not going to have any useful work to do during the cycles in which instruction 2 has not reached it. So at cycle 2, if we stop the time at cycle 5, and we look at what the processor pipelines are doing at cycle 5, the write back stage is applying the results of instruction 1 back to the register file. It's doing that useful work. At cycle 5 decode stage is also not doing anything. It's still holding the instruction 2. So let's move on to cycle 6. At cycle 6, write back has finished. If we stop time at cycle 6, write back stage has finished, so it's not doing anything. The application of the results of instruction 1 to the register file is done. At cycle 6, the decode stage is finally doing work for instruction 2. So data is being read from the register file, all that stuff. But if you look at what's happening at cycle 6, The execute stage don't have anything to do. Memory stage doesn't have anything to do. Write back stage doesn't have anything to do. I mean, there will be electrical signals moving through this pipeline, but they won't be contributing to the forward progress of the program, because instruction 2 has been stuck here for 4 cycles now, depending on how you count it. And this is so the state in which a pipeline stage is not doing any useful work is called a pipeline bubble. So at cycle 6, we have 3 pipeline bubbles inside the pipeline, because there are 3 stages that are not doing any useful work. And we want to reduce the number of pipeline. I mean, one of the big goals in processor design is we want to reduce the number of bubbles as much as possible, because that represents performance degradation, because we're not using the circuits that we've built in the most useful possible way. Yes, and that's the big problem with this stalling approach. It sacrifices too much performance because we're introducing too many pipeline bubbles. And too much is of course, it's a very subjective word. And as an aside, I'm going to say that some processor designers may make this decision, as opposed to some of the more involved, complicated methods we're going to talk about in the next couple of slides, which gives us higher performance, because processor design is always an issue of trade-off between how much circuit space we want to assign to each of these things. Maybe according to some data-driven design that some architect is going to do, this number of bubbles is kind of okay, because this instruction pattern is not going to show up as often in the particular application that they're looking at. Or they want to be as stringent as possible with circuit space, so even handling more complicated ways of handling hazards is something they don't want to do. So this is not necessarily saying that stalling is a objectively bad thing to do. It's just, I guess, know the trade-offs. It's one of the simpler ways to handle read after write hazards, but it can degrade performance. As an aside, it will not degrade performance at all if this data dependency pattern doesn't happen at all. For example, if every single pair of instructions inside this particular program that you write if you have register dependencies, if an earlier instruction writes to a register and the later instruction reads from a register, but these instructions are always more than, say, 5 instructions apart, 5 cycles apart, we will know that by the time instruction 2 reaches the decode stage, if instruction 1 has happened 5 or 6 instructions ago, we will know that the results of S0, well, there are lots of caveats here, but it is possible to write instructions that avoid the read after writes hazards most of the time. So anyways, the thing is, it sacrifices too much performance. Just how much performance? As giving it a kind of a lower bound on performance. Let's see. We can apply Little's law to it again. So in the worst possible case, if every instruction pair has a read after write hazard, which has to be dealt with, there will always be 3 pipeline bubbles inside the pipeline. So at most, we're going to have 2 instructions in the pipeline being processed. So Little's law, saying describes the relationship between the number of requests in the pipeline, L, the performance, the throughput, lambda, and the latency, W. So we can in this scenario, we will have at most 2 instructions in the pipeline. Well, at least 2 instructions in the pipeline. This is in the worst case. At least 2 instructions in the pipeline, and because of the latency of the pipeline is 5, the throughput we're going to get is 2 over 5. In the worst case, of course, like I said, if the program is organized in a friendly way, we can also, it is possible that we will always have 5 instructions filling the pipeline doing useful work at any given time. But in the worst case, we're going to get a throughput of 2 over 5, which is less than half, compared to the ideal performance that we want, which is 1. So that is that. So, and here's the slightly more detailed walkthrough. In the case of stalling, we have 2 instructions again, the add immediate 0 to 1, add immediate S0 to 0. So at the first cycle, we have instruction 1 in the fetch stage. So the fetch stage is going to send out a memory read request to the memory system. At the second cycle, the first instruction has been read. It's in the decode stage. It reads the 0 register, etc. Cycle instruction 2's memory read request has been sent out. At the next cycle, the instruction 1 has reached the execute stage. It's calculating the results of 0 plus 1. Instruction 2 has now reached the decode stage, but the processor is going to keep it there until S0 is applied. And at the next cycle, the instruction 1 is allowed to move forward with this computation, but as instruction 2 is stuck there, introducing a pipeline bubble into the execute stage because the execute stage doesn't have any useful work to do right now. At cycle 5, instruction 1 has been allowed to move forward again to the write back stage. So it's issuing a combinational electrical signal to write the results of S0 to the register file. This is the cycle in which the add immediate result, so 1, is moving through that debugs and all that stuff inside the register file so that it can be available at the next cycle. So at cycle 5, instruction 1 has reached the write back stage, but the value of S0 as visible from the register file has not been applied yet, because if you remember the write results, the state changes are only visible to the rest of the circuit at the next cycle. So now we have 2 pipeline bubbles. At the next cycle, instruction 1 has finally retired. So as the value of S0 as visible from the register file is now finally 1. And the processor management circuit knows that it can stop stalling and allow instruction 2 to start moving forward. So instruction 2 now finally reads the correct S0 and is allowed to move forward into the next pipeline stage in the next cycle, in cycle 7. So in cycle 6, we see that we have introduced 3 pipeline bubbles into the 5-stage pipeline. So we have 5 sub-entities inside the processor, which in the ideal scenario, we want all of them to be doing useful work at every given cycle. But unfortunately, due to this hazard and how we're handling it, in the worst case scenario, in the worst state, only 2, maybe if there's an instruction 3 inside the fetch stage, if there's an instruction inside the fetch stage, only 2 instructions, only 2 stages are doing any useful work in the worst case scenario, which is not an optimal use of processor resources, of silicon resources. So let's try to figure out if there's a better way to do this. Better depending on the trade-offs you're willing to make. So the second solution is forwarding, also called bypassing. In the forwarding method, we introduce a combinational path from the execute stage to the decode stage, so that the execute stage can, within the same cycle, forward its results to the input of the decode stage. And let's look at the drawing. Yeah, so we now have a combinational path. Notice that it's a combinational path, which is visible inside the save cycle, because there's no pipeline registers, there's no pipeline FIFOs on this path. And from the decode stage's point of view, if in addition to stalling, because even this is not going to catch all the possible scenarios, in addition to stalling, if the forwarded results. So the execute has to forward which register index that this current instruction in the execute stage, which register index it's going to write to eventually, and the value that it's going to write to eventually. So from the decode stage, at most, it's going to read from 2 register file locations because that's how RISC-V is designed. And if any of the 2 register file read requests are the same as the one bypassed register write, so if instruction 1 writes to S0, and if instruction 1 is stored inside, let's walk through the time step. Yeah, instruction 1 is in the fetch. Instruction 1 is in the decode stage. It reads S0 and S1 and S2 from the decode stage. In instruction at cycle 3, instruction 1 calculate S0, the results of S0, and the results of S0, which is whichever value it is, along with the fact that this instruction 1 wants to eventually write to S0, so these 2 pieces of data, S0 and the add results, are forwarded to the input of the decode stage. So when instruction 2 reaches the decode stage, when instruction 2 is in the decode stage, it wants to read from S0 and S4. So the processor circuit checks that instruction 2 wants to read from S0. And at that particular cycle, because it's a combinational path, this forwarding results is only available during this cycle. At this particular cycle, the execute stage is forwarding to the decode stage the fact that the instruction that it's currently processing is going to write to S0 eventually, with which value. So when the decode stage wants to read from S0 and S4, instead of using the value that is actually read from the register file for S0, it uses the value that is being forwarded to it from instruction 1, so that it can have correct data, so that we don't have to have pipeline stalls. We don't have to lose performance. We don't have to get wrong results. A caveat here, and this could look like, it's the best possible scenario. The caveat here is from the perspective of this simple forwarding implementation, this is kind of a friendly kind of an instruction layout. Instruction 1, instruction 2 are back-to-back, so that when instruction 1 is inside the execute stage, instruction 2, which depends on the instruction 1, is inside the decode stage. But what if there was a third instruction between instruction 1 and 2? In that situation, when instruction 1 has now moved to the memory stage, and there is no forwarding path from the memory stage to the decode stage, because at least for now, we have only introduced the forwarding path between the execute and the decode stage. Instruction 2 does not have access to the forwarding data of instruction 1, because at this point in time, if there was another instruction between instruction 1 and 2, that third instruction will currently be inside the execute stage. And if instruction 2 doesn't depend on this third instruction, then this forwarding path is not helpful at all. Let's see. But it is true that it does help. It absolutely helps in many cases. But it may still require stalls for a deeper pipeline microarchitecture. For example, if execute takes many, many cycles, for example, if you want to have a integer division, even worse, if you want to have floating point division or something like that inside the execute stage, we're most likely not going to be doing that within a single cycle, because that's a very, very long combinational path. And if execute took many cycles, then if instructions are back-to-back, even if instructions are back-to-back, the forwarding data is not going to be available until all of the sub-pipelines in the execute stage are done. So in that case, instruction 2 still has to stall for a little while. It may not have to stall until everything is applied at the write back stage, but it still has to stall for a little while. And there are other examples, like the one we talked about in the previous slide, which may require stalls. So we can't get rid of stalls entirely. Another thing is that it does also add a combinational path from execute to decode. So the results of the execute has to be combinationally moved to the decode stage. So the critical path of the decode stage now also depends on the critical path of the execute stage, because only after the execute stage completely finishes, or at least the parts that are required to generate this forwarding data completely finishes, can at least some of the decode stage execution take place. So here's a subdiagram below. Now we added this new dependency. A little bit more circuits are going to be required to move forward the data from the execute stage to the decode stage. And from the decode stage, it can't, for example, if the decode stage had a very short critical path before, now it has at least as long a critical path as the execute stage, because it has to wait until the results of the execute stage are done before it can finish actually doing all of its stuff. Thankfully, or well, not thankfully, because this is also very dependent on the implementation. Because the forwarding path moves from the end of the execute stage, well, that's not a good thing, but it moves from the execute stage to most likely the end of the decode stage, because basically the only thing that forwarding is affecting, it's not affecting the bit decoding of the instruction, it's not affecting the register file access. The only thing that the forwarding path, the only part of the decode module that depends on the forwarded data is deciding, do we use the register file reads or do you use the forwarding data? So the previous stages don't really depend on the execute stage. So the propagation delay of the execute stage may be hidden somewhat because it's going to be going on at the same time, while the propagation delay of some of the earlier parts of the decode stage. This could be a very big problem if, hypothetically, if the forwarding path created a dependency at the beginning of the decode stage. For example, I can't think of why that would be required right now, but in some convoluted reason, if the bit decoding of the instruction depends on some calculation results of the previous instruction, then this path will move to the beginning of this propagation delay path. In that situation, the latency is going to be additive because we need to do all of this first, which needs to be forwarded to the beginning of this timing path, and only after that is done, the forwarding is done, the rest of all of this processing can begin. So the latency is going to be additive. It's going to be not any better than if the execute and decode stages are just non-pipelined at all, if they're just the same pipeline. They're just clubbed together in the same stage. I guess that's another reason that ISA design is quite important, because I can totally imagine, if we're not careful, building ISA semantics where decode actually depends on the results of an execute from before. But thankfully, most sane ISAs don't do this. So because it doesn't really introduce a additive latency, because the combinational path doesn't create too much dependencies, the latency of execute and the latency of decode can mostly be overlapped. So it doesn't create, it doesn't add latency too much, and it doesn't create an imbalance in the pipeline too much. An interesting question here that I kind of glazed over so far is, how can hardware detect hazards? How can hardware detect read after write hazards? Because all of this detection and forwarding, all that stuff needs to happen within a single cycle. The decode stage can't afford to say every cycle, let's send a read request response to the later pipeline stages, because that's going to take multiple cycles. So yeah, that's the answer to this question is going to come up in one of the later slides, later lectures, because that's also another interesting design point. Because we're always looking at these two sets of programs. We look at this example again, add immediate and then add immediate. In the first cycle, instruction 1 is injected. In the second cycle, we do the decode for instruction 1. Third cycle, results for I1, instruction 1, is forwarded to the decode stage, so that S0 stored inside the register file is still 0, but the instruction 1 results are forwarded to instruction 2, so that's good. And then we can keep moving forward without introducing any pipeline bubbles. Right. And the reason forwarding is possible in this particular situation is because the answer that instruction 2 depends on, the fact that S0 equals 1, exists somewhere in the processor. In cycle 3, when instruction 2 needs that result, instruction 2 needs the correct value of S0, and the correct value of S0 exists somewhere inside this processor, because luckily at cycle 3, instruction 1 has just finished calculating the results to S0. So forwarding is possible without losing any performance. And like we talked about in a couple of slides ago, if say the execute stage required 2 cycles, and at cycle 3, the answer to S0, what S0 should be, is still being calculated, then we still have to stall, because the answer that instruction 2 needs, S0 equals something, is not yet available anywhere in the processor at cycle 3. In that case, we have to stall again, I guess, until cycle 4, when that answer becomes available to some entity inside the processor, which is the end of the execute stage. And if it becomes available, it is possible for us as designers to add a forwarding path from that stage to the decode stage, so that we can reduce the pipeline stalls as much as possible. And this is going to be kind of important, this fact that forwarding is possible only when the answer exists somewhere in the processor, because it's going to come up with the next type of forwarding. So anyways, data paths with hazard detection. And this is a picture I took from the book, the RISC-V book. But I don't really like looking at this, because it's, first of all, it's complicated. It looks complicated, scary, and this is a good way to present the idea, I guess, of what's happening in terms of which signals are moving where. But like I mentioned before, of course, modern processors aren't designed like this, because it's a lot more complicated than this. So it's not very intuitive. And what we will do, I think, hopefully at the next lecture, hopefully at the next lecture, we're going to revisit this with a higher level code representation of how all of this is implemented. And the higher level code implementation is at least partially how actual industry companies do this. So hopefully that'll be a little bit more illuminating. Right. So that was the read after write hazard. There's a second hazard called the load use hazard. Read after write I guess load use hazard is kind of a subset of a read after write hazard as well, because reading after writing is what it's dealing with as well. But it's slightly different from the fact that in the read after write hazard cases that we looked at just now, depended on the results of an ALU instruction. So we were doing some computation inside the processor and then writing it to the register file which at a later point in time. But the load use hazard is slightly different because it deals with the situation where a later instruction depends on a register updated by a previous load instruction. I guess I should have written that down better. So, yeah, when a later instruction depends on a memory load instruction issued by a previous instruction. So here's an example. If instruction 1 loads from somewhere to S0, and instruction 2 uses that S0 value, forwarding doesn't really work here because loads only materialize at write back. Even if we had a forwarding path from the execute to the decode, even if we say had a forwarding path from the memory to the decode, stage to the decode, that will not help with the load use data hazard because the answer to the question, the answer to the load instruction, instruction 1, which instruction 2 requires and depends on, is not available inside the processor at all because it depends on what's going on off chip from the memory system. I mean, the memory system could be on chip as well if it's a cache, but anyways, it's something that is outside the pipeline. So there's really nothing we can do from inside the pipeline because that data doesn't really exist anywhere. So the only architectural choice is to stall. So yeah, I just wanted to mention here that yeah, there are read after write type hazards that are not completely solvable with the forwarding approach. So yes, here's a walkthrough example. We have the instruction from before, load and then add immediate. At the first cycle, instruction 1 is injected to the fetch. Memory read requests are sent out. Second cycle, instruction 1 moves forward to the decode stage, reads S2, because that's what the instruction depends on. Third cycle, instruction 2 now has to be stalled until S0 is updated because the answer to what value should S0 be is not available inside the pipeline. The execute stage doesn't know because all the execute stage is doing right now is just calculating what equivalent to add immediate is to calculating the actual memory address. So it's adding the values inside S2 to the memory offset, which is 0 in this case. So the execute stage is calculating the memory address from which to read from, but it doesn't know what data is actually going to be read from the memory. So the answer to what value should S0 be is still nowhere inside the pipeline. So instruction 2 has no choice but to stall. So same as before, only after the memory stage sends out the memory read request, and then it is received, the memory response is received by the write back stage. And only after this instruction completely retires and the write back is applied so that S0 has the correct value that we want. Let's say the value is 1, which is read from memory. Only after this, instruction 2 can actually read the correct S0 and then continue moving forward. So we're back to the same situation as before. We have 3 pipeline bubbles. Performance would be, in the worst case, 2/5, all that stuff that we want to avoid. But unfortunately, for load use data hazards, there's really nothing we can do architecturally. From the processor's point of view, there are many things we can do architecturally outside the scope of undergrad computer architecture. But in this pipeline implementation that we have, there's nothing we can do. The only thing we can do is stall. Yes. Forwarding is not useful because the answer exists outside of this pipeline. A non-architectural solution is to have the code scheduled in a friendly manner by the compiler. So if we can reorder the code to avoid using the load results in the very next instruction, then we can probably avoid the stall problem. Of course, the hardware circuitry inside the pipeline for doing stalls needs to be in place because we know it's not always going to be possible. And sometimes things like memory read latencies are not predictable, which may, those things might introduce bubbles and pipeline issues as well. So we do need to always implement stalls. I mean, we do need to always implement the circuitry for stalls so that if there's a dependency, we can handle it. But if we get the compiler, or if we write the code in a friendly way to not have these kind of dependencies very close by, then we can avoid the situation, in many cases. We can avoid a lot of situations in which stalls are necessary. So for example, looking at an example code where we want to do A equals B plus E, and then a completely independently C equals B plus F. These two lines of code, these two statements are completely independent, well, not completely independent, but the second line doesn't depend on the results from the first line, doesn't use A anywhere. They only share B. So if we were to do a straightforward translation of this code, if this first line is translated into a chunk of code, and the second line is also translated into a chunk of code, let's see. Yeah, if we do that, then we introduce a load hazard, because let's assume x2 here is loading B, because B is used in both places. Well, no, let's assume that it's this one is E and the next one is F, I guess, because B is loaded once and then used again. For the add instruction, we can have, if the add instruction comes immediately after the load instruction for B and then E, then the add instruction needs to stall. Same story for the next instruction. If the add instruction comes immediately after the load instruction, the second load instruction, which is here we're loading F because B has been loaded already to X1. So X2 is loading E, X4 is loading F. So in this, if we do this straightforward translation, we add 2 instances of stalls. But on the other hand, if the compiler is smart enough to do this, if this compiler knows about the, at least at a basic level, what kind of pipelining is going on inside, etc., it is possible to reorganize the code so that the load instruction for loading F into X4 can be moved earlier in code. So it's going to do 3 loads all at once, load, 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 and then do adds. And because loading F into X4, which the first edition doesn't depend on, so there's at least one instruction between loading X2 and then using X2 inside the add. So these 2 instructions are now separated by 1 cycle. So this probably won't reduce, it probably won't remove stalling entirely because that's just 1 cycle, but it will at least reduce the bubbles by 1, because that's at least 1 more cycle in which it's doing useful work, which is load F. Even better, when we're calculating the second addition, most likely the bubbles are removed entirely because all the operands that the addition requires has been already taken care of at the beginning of program execution. So this figure is from the RISC-V book. I don't actually know exactly the parameters they use to calculate these numbers, but the fact is, just by reorganizing the code, you can remove a lot of pipeline bubbles, make the code much more friendlier for the processor to execute, all that good stuff. Right, so compiler does best, but of course it's not always possible. So it's not always possible to depend completely on the compiler to do the right thing. So architectural solutions are also very important. For C, no, that's not the reason. It was just in C99 they required, maybe not 99, even something older than that. In the old C, they required all instruction, all variable initiations to happen at the beginning of the basic block, in beginning of all curly braces. That wasn't something to do with architecture. It was just how the C syntax was designed at the time. Anyways, right, looking back at the problematic example that we talked about at the beginning of the lecture, first we have the very first read after write hazard, because the load address instruction, which translates to load immediate instructions, the results of that have to be available to the second load word instruction, creating a raw hazard. There's another raw hazard because most likely T0 is still not available by the time you reach instruction 3. There's a load use hazard because S0 and S1 are still being loaded by the time you reach the add instruction. And there's another read after write hazard because the add instruction results S2 are not going to be available for the time when we reach the store instruction. And then another interesting thing is load address, LA, is not an actual RISC-V instruction. It's, like we mentioned before briefly, it's a pseudo instruction, which is only available to the assembly code. When you write code with load address in it, and you assemble it using the RISC-V assembler, it is actually expanded to one or more instructions by the assembler, depending on how much immediate data you want to load to T0. So for example, if the offset of data, the data block, the data label, if the address of the data label as it is when it is compiled to a binary file is larger than the 12-bit space allocated for the add immediate instruction, it's going to require 2 instructions to handle. It's going to do the AUIPC instruction, the load upper immediate to the PC, add upper immediate to the PC, and then the add immediate instruction. And this also introduces another read after write hazard because the results of the AUIPC instruction is not going to be available to the add immediate instruction at the very last cycle. So we can see this is kind of a packed problematic example because we have what, 1, 2, 3, 4, 5 instructions here, all of which have a hazard. So this is going to we can kind of assume that this is going to have not a very good kind of performance, because every single instruction is going to inject many, many pipeline bubbles. And this is going to be probably what you're going to be experiencing in lab 2. So yeah, there are other potential data hazards as well. And the rule of thumb, the basic rule is data hazards are dangerous if a temporally later instructions, a later instruction's state access can happen before an earlier instruction's state access, which is typically state writes. So if one instruction writes somewhere and the next instruction reads from that same place, or writes to the same place, that whichever access, and if the order can be swapped, then that causes a problem. And the swapping can happen because of microarchitectural decisions like pipelining. So of course, we looked at the read after write hazards. It's an obviously dangerous hazard because the write back stage comes after the decode stage, as you see on the bottom chart here, because there's a 3-cycle difference between the write back stage and the decode stage. Later instructions can try to read something that an earlier stage hasn't written to yet. So it's an obviously dangerous situation. The second possible scenario is write after write hazard, if you have 2 instructions both writing to the same place. But for the in-order pipeline processors that we're looking at right now, this doesn't cause a hazard because all the writes are happening in the same place in the memory stage, and all the instructions are going to reach the memory stage in order. Another type of hazards that can happen is the write after read hazards. Again, there's no hazards for in-order processors because the write back stage comes after the decode stage. Write back stage comes after the decode stage. So if an instruction that wants to read something comes before the instruction that wants to write to the same place, by the time the write instruction, which comes after, by the time the write instruction has reached the memory stage or the write back stage, the read instruction will be long gone outside of the pipeline. So it doesn't cause any problems for us. But yeah, the later instructions reads cannot come before the earlier instructions writes for this reason, because by the time the write instruction reaches the write back stage, the earlier read instruction will be just completely out of the pipeline already. But it can cause problems if the processor are allowed to reorder the instructions depending on dependencies and whatnot, but that's outside of the scope of undergrad computer architecture. So yeah, for our purposes, this write after read does not introduce a hazard. The final combination is read after read hazards. And of course, because there's no state changes, reordering, nothing actually changes causes any issues. So there's no hazard. So the bottom line is that out of all these 4 possible combinations, the only thing we have to worry about right now is read after write hazards. Although that is not to say that these other hazards are not they're not to say these other hazards are fundamentally safe. It's just that in the sort of like how the read after write hazards suddenly became a problem because we started pipelining things, these 2 other write after write and write after read hazards start becoming problems once we start adding different architectural, microarchitectural optimizations.